Now we're going to look at something called equipotential surfaces. We have this charged particle right here, this positive Q, and it has an electric field around it. And if I go a certain distance out in all directions, there's a sphere that surrounds it that has the same potential at all points. It might be a certain volts. It might be, let's say, 20 volts right there at position D. If I go further out at position B, you might have 10 volts. If I go further, 5 volts, and I go further, it'll eventually be 0 volts when I go out to infinity. These are called equipotential surfaces. The equipotential at all points along the surface is exactly the same. So as you go from A to B to C, the equipotential is exactly the same, or the potential is exactly the same. So there's no work being done as you go from A to B to C. But as you go from A to D, there will be work being done by the electric field as you move from one position to another. If you look at our picture here, this positive Q, this is an area of higher potential, and this is an area of lower potential. And like I said, if you go further and further out, you start going towards zero potential. Near the positive charge, the potential is high. And the potential surface is perpendicular to the electric field lines. So if you have here a positive charge and a negative charge, you'll see the red lines are the electric field lines. It comes out of the positive and into the negative. And the blue lines are the equipotential surfaces. Anywhere along that blue line, the potential is exactly the same. So if you come over here near the positive charge, this is an area of high potential. Near the negative charge is an area of low potential. And right down the middle, that's probably a potential of 0 right there. So this might be 100 volts. This might be negative 100 volts right here. So you have 100 volts here on this blue line, negative 100 volts on the other blue line near the negative charge. So if you're here at 100 volts and you go out further, it's probably like 90 volts, 80 volts, 70 volts, 60, 50, and so on. You start hitting towards 0 volts. And the same thing here, we're in the negative. You start at negative 100, negative 90, negative 80, negative 70, and it starts moving towards 0 volts as well. This idea leads to a new equation that the electric field here, E, is equal to the change in potential all over the displacement. It's the rate that potential changes. That negative sign just tells us that that positive charges move from areas of high potential down to areas of negative to low potential, and so that negative sign is not necessary. The E is the electric fields in newtons per coulomb. The delta V is the difference in potential V, that's volts. Delta S equals distance between equipotential lines. So it's like a gradient. It's how quickly does potential change over a distance. So here we have a situation where the plates of a capacitor are separated by a distance of 0.032 meters, and the potential difference between them is negative 64 volts. Between the two potential surfaces shown in color. And the potential difference between them is negative 64 volts. Between the two equipotential surfaces shown in color, there is a potential difference of negative 3 volts. So here's our the blue here, the light blue, is the negative 3 volts, and we want to find the spacing between the two colored surfaces. So we're going to have to find the electric field between these two plates, and what we need to know about a capacitor or a parallel plate capacitor is that the electric field in between that parallel plate capacitor is constant, never changes. So you can find the electric field from the first information that we're given, and then you can go ahead and find, using that same electric field, because that electric field stays constant the whole time between the two plates, find the distance between those two surfaces. So here we have it. We found the electric field between the two light blue plates, which was a negative 64 volts or 0.032 meters, giving us 2,000 volts per meter. And then we use this equation again, but now for a different distance, for this shorter distance that we wanted to calculate. We knew the difference between those two plates was negative 3 volts, and the electric field was 2 times 10 to the 3rd volts per meter that we calculated earlier. So the change in displacement between those plates is 1.5 times 10 to the negative 3 meters.